Okay, so we would like to introduce double integrals and show a simple computation. So basically the idea is that if we have a function defined over a 2D domain, then a double integral computes the volume of the region between the domain of definition on the xy plane and the graph of the function. And we have the usual convention that we have in regular integrals, that if part of the region is below the xy plane, then it counts as negative. Now, the easiest integrals to compute, or in some sense, our general goal, is to be able to express an integral as an iterated integral. What we mean by that is an integral where we integrate with respect to one variable, and that integration gives us a simple integral in one variable, sorry. So this is always the easiest thing to do if the domain of definition is a rectangle. And let's explain this notation. So the notation in general, AB cross CD means that we have all x and y's, where x is between A and B, and y is between C and D. This is a rectangle, and we can even sketch it in order to understand what it looks like. So let's say that here's AB, and here's C and D. Then this is what we're looking at. Here's our rectangle. In this case, whenever we have an integral over this rectangle of presumably a continuous function, we're not going to be interested in this course for discontinuous functions. Then this can be written as an iterated integral in two different ways. So this will be the integral of f of xy, and we do integration first with respect to x. What this means is that we treat y as a constant, same thing that we were doing when we were taking partial derivatives in some sense, and this goes from a to b, and what we get depends on y, meaning it's a function of y, it's an expression of y, and we integrate from c to d. Or we could go to an integral first with respect to y, and then with respect to x. So these are called double iterated integrals and should be considered as means of computing integrals, double integrals. There are some interesting cases in which one integration will be more convenient than the other, one way of integrating. But we're going to see more notable examples of that when the domain of definition is not a rectangle. We said in the very beginning that eventually we will be interested in general domains of definition. However, this first example that we're doing is for a rectangle. And let's solve it now. After we've given this information, let's solve our example. So we have the double integral over 0, 1 cross 0, 2. And the function was x plus y squared dA. Here the letter A stands for area, and it's a good way to distinguish between double integrals and double iterated integrals. So I'm going to write it write the integration first with respect to x, And for that, I need to make sure that I choose the first component, 0, 1. So I put from 0 to 1 of x plus y squared. And then I go from 0 to 2 dy. And I carry out the first integration as if y was a constant. So what would the antiderivative be? X squared over 2 plus the constant y squared times x. If you had 7, the antiderivative would be 7x. You have y squared, the antiderivative is y squared times x. And here this will go from 0 to 1. What sometimes people do is they write from x equals 0 to x equals 1. I don't necessarily like to adopt this notation, but it's sometimes helpful in order to distinguish what is being substituted. So let's substitute 0 and 1 and see what we find. And so we will find 1 over 2 plus y squared. And then the other two are 0, so we would subtract 0, so we omit that. And we now finally get an integral that we hand to our friend who takes Calc 1 or Calc 2, because it's an easy integral to compute. So this will give us 1/2 y plus y cubed over 3. And we want to go from 0 to 2. So this will give us 1/2 times 2 plus 2 cubed, which is 8 over 3. So this will be 1 plus 8 over 3, which is 11/3. And of course, we omitted the minus the 0 part. And that's the final answer, and that completes the computation of our double integral. Thanks for watching.